Hello everyone. Welcome to this, our first lecture of the fourth week. And today we're going to start talking about random variables. So far we've been talking about real events. Real events are things like the flip of a coin results in a head. It's raining outside at the moment, or another event might be that the load on a system exceeds the critical value, and so on and so forth. These are all fine. This is the fundamental idea behind probability theory, but we generally want to use mathematics, and so we often have to map these real events to numbers so that we can make use of mathematics. So that's the basic idea here. An example is, suppose we have a bucket that contains apples and oranges, which are being selected randomly in a series of trials. So I reach in, pick something out, and it can be an apple or it can be an orange. So we're going to do a mapping here. We'll let the random variable x sub I, and random variables will use capital letters. So the I here is the ith trial, and x is either 1. If an apple, let's suppose that if an apple is selected, we'll let x equal 1, and 0 if an orange is selected. So this is a map from the real events, which is to say selecting either an apple or an orange from the bucket, to a number, either 0 or 1. And so now we can make use of math. For example, we can make use of the familiar summation operator. So the sum I equals 1 to 30 of xi is the sum of x1 plus x2 plus ... plus x30. And so we're talking about 30 trials here, and each trial will either be a 0 or 1 depending on whether an apple is picked or not. If a particular realization of the experiment yielded, say 0 for the first one, that means I didn't pick an apple. 0 for the second one, I picked an orange. 1 for the third, so I picked an apple here. 0 for the fourth, so I picked an orange. 1 for the fifth, I picked an apple, and so on and so forth. And let's suppose the sum of those 30 numbers gives me 19. Then what has actually happened inside this experiment? Well, we can see the ones correspond to apples being picked, so if I have them all adding up to 19, it means I picked 19 apples out of the 30 trials that I had. And therefore I had 11 oranges picked. So as I mentioned, we'll represent random variables using capital letters and known values or realizations using lowercase letters. I've put realizations in red letters here. Once we've performed the experiment, we know the outcome of the experiment, and it's no longer random. We know what the value is, and we call that a realization of the random variable. And but the next experiment, which if we haven't done it yet, we don't know what that random variable's value is, so it's still random, and x is still capital. So just remember the distinction. Little letters correspond to realizations or known values, and big letters correspond to random variables. So, for example, the height of a particular person is currently unknown, and so is a random variable x. Once I've measured that person's height, it is no longer unknown, and you've measured the value, so it is a known value, little x. The main thing to remember is that capital X is unknown. Okay, so we're uncertain about what its value is. And in fact, the most we could say about x is what its probability is of taking on any of its possible values over the sample space. We call this a probability distribution. So let's illustrate this with an example. Let's let x equal the outcome of the roll of a die. Well, we know a die has 6 sides, so the sample space is the numbers 1, 2, 3, 4, 5, 6. And the complete description of the random variable x is its probability distribution. In this case, we call this a probability mass function, or PMF, since this random variable happens to be discrete. We'll define discrete a little bit more carefully in a few minutes, but basically, if there's a countable number of outcomes, we call it discrete. Now we know if this is a fair die, then the probability of getting a 1 is just 1 over the number of possible outcomes, 6. So 1/6 for x equals 1, probably x equals 2 is a 6, and so on and so forth. And we call this set of 6 numbers a probability distribution. And note that these 6 numbers, since they span all possible outcomes for this particular random variable, they must all add up to 1. And we may use the assumption here that the 6 outcomes are all equally likely. Okay, let's consider another example. Let's look at the sample space consisting of the outcomes of 3 coin tosses, and let x be the number of heads shown. Okay, so this is another mapping. The actual events that take place are shown on the left-hand side here. We can have HHH, HHT, and so on and so forth. And then we map these things to the number of heads showing, so the HHH gets mapped to the number 3. HHT gets mapped to the number 2, as does HTH and THH, and so on and so forth. We can map all of these real events on the left-hand side to numbers on the right-hand side. And then I guess we can talk about what is the probability distribution of our random variable. We know that x, before we perform this experiment, x is unknown, and so the most we could say about it is what is its probability of taking on each of its 4 possible values. I guess I could compute the probabilities down here. I've shown it up here already. We can kind of see this, that the probability that x equals 3, that corresponds to only one particular event in the sample space S. And all of these events in the sample space S, there's 8 of them. They all have the equal likelihood of occurring, so they're all probably 1/8. What that means is that the probability that x equals 3 is just equal to the probability that I got HHH, which we know is 1/8. But the probability that x equals 2 has 3 events that lead to this. Okay, we could have HHT, HTH, or THH. They each have probability 1/8, and they are disjoint. If I got HHT, I could not have got HTH. So the probability of getting to 2 is just the sum of these 3 probabilities, which gives me 3/8. Similarly, for the probability that x equals 1, I get 3/8. And for the probability that x equals 0, there's only one outcome leading to that, and it is probably 1/8, so that's 1/8. And we could check this. These 4 numbers here have to add up to 1. 1/8 plus 3/8 is 4/8, plus 3/8 is 7/8, plus 1/8 is 1. I think I've computed here in more detail the probabilities associated with each outcome in S. Assumes that each of those outcomes is equal likely. We are also making the assumption that the coin tosses are independent. So the event that I got HHH means that I got an H on the first toss, and an H on the second toss, and an H on the third toss. And since they're independent, it's going to be the probability of the first toss times the probability of the second toss being ahead, and times the probability of the third toss being ahead. So probability of H1, probability of H2, probability of H3 multiplied together. And we know that each of those is a probability of a half. So I got a half times a half times a half is 1/8. And so this similarly for all other possible outcomes in S, they're all going to be a half times a half times a half. So probability 1/8. Then we look at the probability that x equals 1. We worked it out already above. We know that this should be just 1/8 because there's only 3/8 because there are 3 outcomes that lead to x equals 1. But in detail, we can write that as the probability that we get HTT or THT or TTH. And then we're seeing unions, so our question we ask is, are those 3 things disjoint? And like I said earlier, if I got HTT, I could not have got THT, so these are disjoint. And that means I can just add up the 3 probabilities and I get 3/8. So the probability distribution is one way of looking at characterizing the random variable. There's another equivalent way of looking at it, and that's the so-called cumulative distribution function. And we're going to define this as capital F of x, evaluated at some specific value, little x, and this is defined as the probability that my random variable x is less than or equal to x. So remember, this is a different way of looking at it. Up here, we had the the distribution consists of 4 probabilities. Each of those are equal. So probability that x equals 3, x equals 2, x equals 1, and x equals 0. But now this cumulative distribution function is the probability that x is less than or equal to say 3 or 2 or 1. And the less than or equal to is why we say cumulative. So as little x gets bigger, this probability gets bigger. So we accumulate probabilities to the left of x as we go along. Okay, so for our 3-coin toss, where x is the number of heads turning up, we can look at various options here. The probability that x is less than or equal to -1, well, that can never happen. The smallest value of x is 0. So that probably has to be 0. Probability that x is less than or equal to 0 is 1/8. Because we're including now 0. So the equality here equal includes x equal to 0. I can move a little bit farther to the right, probably that x equals a half. There's only one value that's less than a half, that's 0. So this is still equal to the probability that x equals 0, which is 1/8. Probability that x equals less than or equal to 1 now has two values in it. X equals 0 is less than or equal to 1, and x equal to 1 is less than or equal to 1. So this probability is equal to the probability that x equals 0 or x equals 1. And then I see a union. I ask if these are disjoint. If x equals 0, it cannot also equal to 1. So these are disjoint. So I just add the probability of this plus the probability of that, which is 1/8 plus 3/8. Gives me a half. So fx of 1 has now increased from 1/8 to 1/2. And then I can look at what happens at fx of 2. This is the probability that x is less than or equal to 2. And this now includes 3 points. So x equals 0, or x equals 1, or x equals 2. And these are again disjoint, so I can just add up the 3 probabilities. 1/8 plus 3/8 plus 3/8 gives me 7/8. fx of 3 is probably that x is less than or equal to 3. Well, we know all 4 numbers are less than or equal to 3. In fact, we can see that means the probability that x equals 0, or x equals 1, or x equals 2, or x equals 3. And add up their probabilities gives us 1/8 plus 3/8 plus 3/8 plus 1/8, which is 1. And as I move little x further to the right, I'm still always, there's no more probabilities to add in. The capital F remains at 1. In fact, we can see this graphically. If we plot capital F, we see that when we hit 0, we jump to 1/8. So I'm showing the filled in dot at 0 at the 1/8 level. Then we move across, we stay at 1/8 until we hit 1. As soon as we hit 1, we jump up to a half. Okay, then we move along at a half until we hit 2, and then we jump up to 7/8, and then we move along here until we hit 3, and then we jump up to 1, and then we stay at 1 forever. So some properties of this cumulative distribution function are, first of all, it's non-decreasing. Okay, so this always increases or stays flat. If it goes down, you know something's wrong, because this is always a sum of probabilities, and probabilities cannot be less than 0. If this was going down, then it means you've got negative probabilities in here, and that's not possible. So this always has to increase as we move to the right. And in fact, if we move infinitely far to the right, this thing has to go up to 1. And if we, in the other direction, if we move into infinite far to the left, it has to start at 0. So this function generally goes from 0 and then starts increasing somewhere and eventually ends up at 1. Okay. Now, for discrete random variables, the cumulative distribution function is of limited use. I don't usually use it, but we'll see shortly that if we know this capital F, we can avoid integrating continuous random variables, and we'll see that shortly. So capital F is very valuable to us later on in this course. Okay, so let's look at another problem. Suppose our experiment now consists of turning on a light bulb and timing how long it lasts before it burns out. The timing here is going to be a number, so that say 12 hours after you turn it on, it fails. And so that's a random variable. We don't know ahead of time exactly when it's going to fail. The sample space for that particular random variable, well, there are now infinitely many possible outcomes. It could fail at any instant in time after it's turned on, and we'll assume that's at time 0. So sample space is any real value of t where t is greater than or equal to 0. I'm including 0. We could fail instantly as soon as we turn it on. So T, capital T is going to be the light bulb lifetime, and since T is random, we need its probability distribution. So we don't know what T is, so we can think of things like probably that T takes on a specific value, little t. So there's a problem we run into right off the bat. Now little t is a real number. And so we could ask ourselves, what is the probability that the light bulb fails at exactly 1.0000 hours after the thing is turned on? Well, there's an infinite number of zeros here. So we're talking about what is the probability that it fails at the instant that 1 hour elapses. So we're talking about a probability of failure at an instant in time. And we know intuitively that the probability that it fails at any particular instant in time is going to be 0. There's too many instances. There's an infinite number of instances in any time interval. So basically we end up with our probability distribution looks like this. Probability that t is equal to little t is 0 everywhere. So this is not very useful. We have to come up with a better way, period, of characterizing these so-called continuous random variables. We know we can determine probabilities of failure within a range of time. So you could say, okay, what is the probability that the light bulb fails between 0.2 and 0.3 hours after it's turned on? And this will be a non-zero probability. There is some chance that it'll fail in that time interval. In fact, if we put 10,000 light bulbs on trial and count the number failing in time intervals 0 to 1, 0 to 0.1, 0.1 to 0.2, etc., we can construct a histogram. We saw those earlier in this course, allowing us to estimate the probability that it fails between 0.2 and 0.3. If we fit a smooth curve to that histogram, suppose we fit little f of t, so this is just a function. We'll see later that this is a probability density function. Let's say it's exponentially decaying, and then I see a histogram that looks something like this. So basically, the number that failed between 0 and 0.1 hours was some value, and then the number that failed between 0.1 and 0.2, a little bit lower, and so on and so forth. Okay, we saw something like this, and this thing appears to be exponentially decaying, so we could fit a distribution lambda e to the minus lambda t to this histogram. In fact, the probability that the light bulb fails between 0.2 and 0.3 is just going to be the normalized area, or the frequency density area inside this block. And in fact, if I then fit this curve, I can obtain this approximation to this area as the integral of my fitted curve between 0.2 and 0.3. Okay, so that's actually the basic idea. We're going to use this idea here to characterize these so-called continuous random variables. So before I go there, let's just talk about types of random variables. So I mentioned discrete random variables where x takes on a countable number of possible outcomes. And we all think of lots of examples of this. Roll of a die, we already looked at. Number of people contracting COVID-19 in Nova Scotia next month. Number of hurricanes this year. Number of years until a particular engineering design fails, and so on and so forth. Note that examples 2 to 4 actually have an infinite number of possible outcomes. Hopefully 2 doesn't, in fact, but theoretically I suppose that it could. But we could go an infinite number of years before a particular engineering design fails. Again, unlikely, but there's no arbitrary upper limit to that number. And nevertheless, we still say that this is discrete, even if we can at least start counting the number of years until a particular engineering design fails. For discrete random variables, their probability distribution is called a probability mass function. I mentioned this earlier. Often I'll just write it as PMF. If there are n possible values, their PMF is the set of probabilities x equals x, probability that x equals x1, probability that x equals x2, probability that x equals xn, for n different values. The cumulative distribution function is defined as the probability that big X is less than or equal to xi. That's my argument here. So I add up the x's that are less than or equal to xi and add up their probabilities. And the other thing is that if there are n possible values, the sum of these probabilities has to be equal to 1. Okay, continuous random variables. In this case, x takes on an uncountable number of possible outcomes. Examples here are time to failure, where time is measured infinitely precisely. Temperature, again, if it's infinitely precisely measured, that's a continuous random variable. Mass of an object is another example. And now, of course, I mentioned that probability that x takes on a specific value must be 0, so we cannot use a probability mass function. Solution, we define probability that x equals x is equal to f of x dx. So I've introduced this, I mentioned this function here. I'm going to call this a probability density function. And this is sort of an approximation to the actual calculus. So basically it's saying the probability that x lies within dx, little dx, of little x is equal to f of x times dx. And so in the limit as dx goes to 0, if we think about the calculus of this problem, this right-hand side go to 0, which is what we expected to see here. But the f of x itself doesn't have to go to 0. And in fact, it's the relative likelihood that x is equal to x, basically. Well, okay, so we're going to call this a probability density function. You'll notice the word density here. For the discrete, we had a probability mass function. So how do we get mass, which is a probability, from density? Well, we know density times volume, it gives me mass. In fact, depending on how density is defined, it could be density times any length measure. It gives us mass, which is a probability. So this density function, f of x, we're going to call that, times the length, which is dx, gives me a probability, the probability that x is equal to x, or within a distance dx from x. But the important thing to note is that this f of x is a density, or a relative likelihood. It is not a probability. So basically, if you're looking for a probability, you always have to multiply this by length measure, and in order to get the probability. So the probability here, here's an example of a f of x probability density function. And here's my 12. The probability that x is equal to 12 exactly is the height of this function times the width of this little block surrounding 12. And that width, of course, goes to 0 in the calculus of the problem. And that means this right-hand side goes to 0, but this height here doesn't have to be 0. In fact, it's saying basically that 12 is more likely to occur than 14, which is more likely to occur than 16, and so on and so forth. And the shape of this thing would come from a histogram. Okay, so let's illustrate this with another example. What is the probability that a light bulb fails between 11 and 12 hours? Okay, so this is the statement of this is the probability that x is between 11 and 12. I put the equality on the right-hand side. Since this is a continuous random variable, it's not going to make any difference to the calculation of the probability. You can put the equality on this side. You could leave it off, but usually I put it on one side or the other. Okay, so strictly speaking, this is the probability that x is equal to 11. 11 point, an infinite number of zeros with a 1 at the end. So we've excluded 11 here, so a little bit to the left of 11. Or x equals 11 point .0 .2, so a little bit more to the right, and so on and so forth, until I work my way up to x equals 12. So I've got a union of all of these possible values of x. There's an infinite number of them in between 11 and 12 now. And so when I see unions, I ask if they're disjoint. Well, yes, they are. If x is 11.000 with a 1 at the end, it can't also be equal to 11.000 with a 2 at the end. So that means I just have to add up all these probabilities. And each of these probabilities is the value here at f of x. So the f of x at 11.0001 times dx, plus f of x at 11.002 times dx, and so on and so forth. And we recognize that this is actually just an integral. So in the end, I get the probability that x lies between 11 and 12 is the integral from 11 to 12 of f of x dx. And in the picture here, that's just the area under f of x between 11 and 12. Well, we've already defined the cumulative distribution function and said that's f of x is equal to the probability that x is less than or equal to x. In this picture here, if this is my little value x, then capital F is the area underneath this f of x between 0, in this case 0 and x. In general, it's between minus infinity and x. The big advantage, as I mentioned, to capital F, the cumulative distribution function, or CDF, is that if we know it, then we don't have to integrate. And you'll find f of x is provided in our summary pages for all of our common distributions. So basically, if we knew the f of x for this problem up here, this one here, then I can compute probably that x lies between 11 and 12 as the area under the PDF up to 12. That's the green hash part, and that's the f of x of 12. And then I subtract the area under the PDF up to 11. So that's the red part. And I'm left then with just the area between 11 and 12. So f of x of 12 minus f of x of 11, it gives me this probability. And again, if I know those functions, I don't have to go to this, where's my integration? Here. I don't have to do this integration here. Okay, I mentioned earlier properties of the cumulative distribution function, or CDF. In general, as I mentioned, it's defined as the probability that x is less than or equal to some specific value. So in general, that's an integral from minus infinity to x of f of x at some dummy variable, I'll call it s, ds. If we know capital F of x, can we retrieve little f of x? Well, it turns out we can, because capital F is an integral of little f, then little f must be a derivative of capital F. And so we can get that. If we know capital F, we can get the little f. Okay, let's look at an example. Three-coin toss again. We saw earlier probably that x equals 0 is 1/8, x equals 1 is 3/8, 2 is 3/8, and 3 is 1/8. That adds up to 1. Our probability distribution function looks like this. So we've got 1/8, x equals 0 is a little bar of height 1/8, x equals 1 is a bar of height 3/8, and so on and so forth. We saw earlier that our capital F of x goes up in these step-like functions. Well, it turns out that I can recover little f in the discrete case as the amount of stepping, so the increase here. So in fact, probably that x equals 0 is the height of this thing. That's coming in here. Probably that x equals 1 is the distance between this line and this line. So it's f of x1 minus f of x0. Probably that x equals 2 is the distance between here and here. It's f of x2 minus f of x1. And probably that x equals 3 is f of x3 minus f of x2. So again, we can recover, if I know this picture here, I can recover these probabilities here. And I've just worked through the math here. Where is it? Yeah, okay, so probably that x equals 1 is a half minus an eighth, which is 3/8, so we knew that before. Probably that x equals 2 is now 7/8 minus a half, that's 3/8. And I could do the same thing here. Probably that x is equal to 3 is 1 minus 7/8, which is 1/8. Okay, and I think I already mentioned these properties. F of x has to lie between 0 and 1. At the right-hand end, it's got to go up to 1. Left-hand end, it's got to start at 0, and that it's non-decreasing. So the main thing to remember here is that the capital F of x is a probability, whereas f of x is not, and capital F of x is very useful to allow us to avoid integrating. So that concludes this. I think this part 1 of the first lecture of week 4. And I'll see you shortly for the second part. Thank you.